Okay, so now let's do a couple more examples with these functions. Example number 24. Example number 24 is let y be equal to this set as n squared such that n belongs to n, the set of natural numbers, which is a subset of the natural numbers. Now consider f a function from n to y, so this is basically y, the same set, as f of n is equal to n squared. As f of n is equal to n squared. Show that f is invertible. Show that f of n is invertible and find the inverse of f. And find the inverse of f, right? So now in order to solve this problem, so you see that this y is basically the codomain of f, right? And that is basically all the perfect squares that in the set of natural numbers, meaning that 1, 2, 4, basically 9, 16, 25, and so on and so forth. And the domain of f is basically the set of natural numbers. And the rule that defines the function f is f of n is equal to n squared, meaning that every natural number starting from 1 is mapped to the square of itself, meaning that, for example, 1 will be mapped to 1, 2 will be mapped to 4, 3 will be mapped to 9, and 4 will be mapped to 16, and so on and so forth. This is the set of and so on and so forth. So this would be the set of natural numbers, the domain of the function, and this is the set, y, which is basically this set over here, right? So you want to show that f is invertible. So in order for f to be invertible, first of all, f has to be 1, 1, which it is. There is no problem with f being 1, 1. Every distinct element of n has a distinct image in y. So you can say that f is 1, 1. And also f has to be basically onto or surjective, meaning that every element of this set y has to be the image of some element in the set of natural numbers, which is also the case. There is no problem with that. So f is basically both 1, 1 and onto, meaning that you can actually find a function which allows you to get back from each of these elements back to the element that you started with. That would be the inverse process of f. So f takes you from here to here, that is f, and then, for example, some other function g, for example, or any other function, you can call it anything. G takes you back from basically, for example, you can say that basically, for example, f takes you from 2 to 4, and then g takes you from 4 back to 2. So these are two, and that's basically why we say that g is f inverse. G is equal to f inverse. It's the inverse process of f. Now, in order to in order to show that f is invertible, we need to show that based on the definition that we had, we need to show that basically we need to show that if f is a function from x to y, we need to show that if f is a function from, for example, x to y, any two sets will do. There exists a function, say for example g from y to x, such that g of is equal to I of basically x, and f of g is equal to I of y. If we can show that, then basically you can call basically g would be called the inverse of f. Then g could be called the inverse of f, denoted as for example f inverse or something, or you can call it f inverse, you can call it g, but knowing that g is basically the inverse of f. Now in order to do that, what I can do is that you can consider any arbitrary element y belonging to the set belonging to y. Now by the definition of y, basically any element, well, we can of course this is not called y here, so I could say that basically any arbitrary element n squared belonging to y. By the definition of y, well, of course n squared is okay. So now to solve this problem, I'm going to make some changes here, because here we are dealing with n and n squared, and so I'm going to just simply rewrite this, because I tried to solve the problem this way. It's trouble to solve it this way. I'm just simply going to make some changes here, not to the problem itself, but to the notation. So I'm going to write it as let y be equal to, for example, some set, some set y is equal to x squared, for example. Instead of n squared, I'm going to write x squared, such that x belongs to the set of natural numbers. That's the same set, but I'm just writing it this way, so there is some way to talk about it, which is a subset of the set of natural numbers. Now consider f, a function from n to y, as f of, I'm going to write it as f of x is equal to x squared. right? The same thing basically. You want to show that basically you want to show that f of x is invertible and also find f inverse, the inverse of f. So now in order to solve the problem, what you can do is that you can consider some, this is the solution, consider some arbitrary basically element y belonging to the set y, and by the definition of y, by the definition of y, basically y is equal to x squared for some basically x belonging to the set of natural numbers. And remember that these are absolutely important. For example, x belongs to what, y belongs to what, and all of these are absolutely important. Usually what you see, not usually in books, I mean basically in good books related to mathematics, what you usually find is that all of these things are well defined, and the definitions are taken care of, meaning that, for example, x belongs to the set of natural numbers, or y belongs to that, and so on and so forth. These are actually taken into consideration in the problem, but there are even some books in which there is no definition. They just give you, for example, some function as, for example, f of x is equal to x squared plus 5, and you're supposed to find the inverse of this function. You don't know what is the domain of this function, you don't know what is the range of this function. What they usually do is that they say that, okay, so this is a function of x, so they write it as y is equal to x squared plus 5, and then find x in terms of y, so x squared is equal to y minus 5, so x is equal to, for example, the square root of y minus 5. And of course it's supposed to be plus or minus depending on what you're doing, and then there is no way to decide, for example, whether x is equal to, whether you should write x as, for example, the square root of y minus 5, whether you're supposed to write x as just simply the square root of y minus 5, the square root of y minus 5, or the plus or minus square root of y minus. So depending on the restrictions imposed on your problem, you might get the plus or minus, or you might not get it. So you need to be careful about that. And of course, in the problem that we have, basically all of these things have been taken into consideration, so it's actually possible to decide what to do when you want to take the square root of something, or when you want to raise something to the second power, and so on and so forth. Okay? So every problem must be defined properly, and those definitions then must be taken into consideration while you're solving the problem. So what now, if I consider some arbitrary element y belonging to y, by the definition of y is equal to x squared for some natural number, for some x belonging to the set of natural numbers. Now, since I have since I have y is equal to x squared, so then if I take the square root of both sides of this equation, the square root of y is equal to the square root of x squared. And as you can see over here, now as I'm taking the square root of these two variables, it's important to know what is the domain of the square root function in each case. So as you can see, y is basically x squared, and this is basically based on the definition of y. So the definition of y is telling me that x belongs to the set of natural numbers. That means that x is a natural number. So when you raise a natural number to the second power, you're always going to get, of course, a positive natural number, which means that then y also, since y is equal to x squared, y also is a positive natural number. So when you take the square root of a positive natural number, then you don't have to write plus or minus y, because it's just simply not necessary. That simply means that you're taking the square root of, for example, 16. So the square root of 16 is the square root of 16 is just simply equal to of course it's equal to plus or minus 4, right? But it's important to know what number you used in order to get this 16, and now you're taking the square root of that. So the number that I used in order, and I squared that number in order to get y, that number was basically a natural number, right? So that means that when I'm taking the square root of y, then I'm not going to get the negative side, because x to begin with was a positive number, and then what that means is that then the square root of y becomes simply y. Otherwise the square root of y could be plus or minus y. So these things are important when you're solving the problem, right? So what that means is that, so then based on that, I can simply write the square root of y as y, and the square root of x squared, I can simply write it as, the square root of y actually remains the square root of y. I cannot simplify that, but then the square root of x squared is going to become just x, and not plus or minus x, right? Now, once you know this, you know that x is equal to the square root of y, which means that based on this you can define a function. Now based on this, you can define a function. Say for example g of y, which is equal to the square root of y. So as you can see, the function that we had, the function is just simply a squaring function, meaning that whatever you give to that function, it squares it. And the function that we got here as the inverse of that function, of course we haven't proved yet whether the function is actually the inverse of that function or not. We will do that in the next steps. But if that's the case, then it makes sense that the inverse of a squaring function is a square root function, meaning that whatever you give to this function, it's going to square it for you. And then, meaning that, for example, you give a 2 to this function, to f, basically, if you give a 2 to f is going to square it for you, and it's going to give you a 4. Now the function, which is basically the inverse of f, is supposed to take this 4 from you and give you back the 2 that you gave to f in order to get the 4. Meaning that when you get the 4 and give it to g, then g is supposed to square, to take the square root of that, and the square root of 4 is equal to 2. So that means that you got, whatever you gave to f, to get 4, when you gave 4 to g, you got the same thing, right? So that is basically the meaning of this, the inverse function. So what that means is that now, based on this equation that we got here, we can define a function, say for example g of y is equal to the square root of y. Now we need to make sure make sure that basically f or g of f is equal to I of the domain of the function f, and the domain of the function f was the set of natural numbers, which means that g of f is an identity function on the set of natural numbers. And we also need to make sure that f of g is an identity function on the set y, because y is the codomain of f, basically I of y. So in order to check whether these two are actually the case, you can write g of f is equal to g of f of x. Now g was basically the square root of y. So the square root of, now what is f of x? F of x is equal to x squared. F of x is equal to x squared. Now again, when you take the square root of a number, you could get a positive number, you could get a negative number. But again, since x belongs to the set of natural numbers, then that means that basically the number that you started with to get x squared was a positive number. That means that normally you would get plus or minus x, for example, but in this case, of course, you get only plus x, which means that basically g of f of x is equal to x, which implies that basically g of f is equal to I of I of the domain of the function. The domain of the function is the set of natural numbers I of n. Now we need to also check whether f of g is the f of g is the identity function and the codomain of the function. So f of g is equal to f of g of x. Now you know that f of x is equal to x squared, and g of y, and that's supposed to be y, of course. G of y is equal to the square root of y. So then f of x is equal to x squared, so you will get the square root of y. You will get the square root of y whole squared. Now when you are basically raising the square root of some number to the second power, there you need to be careful, meaning that y over here is basically some number which belongs to the set of natural numbers, and the way that you get y is that basically you raise x to the second power to get y. That means, and that x also belongs to the set of natural numbers. So that means that when it's just like, for example, suppose that you get the square root of 25. So the square root of 25, of course, can be plus or minus 5, meaning that 5 squared is equal to 25, negative 5 whole squared is also equal to 25. And therefore you can say that the square root of 25 is equal to plus or minus 5. But again, here, because x belongs to the set of natural numbers, whatever y you get as a result of squaring x, that y, you obtain that y as a result of squaring basically as a result of squaring a natural number, which means that again the square root of y whole squared is just simply going to give you y. And it's going to be a positive natural number. So that means that whatever you give to that means that basically FOG of y is simply going to be equal to y, which means that whatever you give to FOG, basically as long as it belongs to the codomain of the function, which is basically the set y, you are going to get back the same thing. You give it any y, it will give you the same y back, which implies that basically FOG is equal to I of y, and therefore you can say that basically G of y, or you can, let's say it this way, you can say that therefore f is invertible. You can say that f is invertible, and f inverse is equal to basically f inverse of x is equal to G of y, which is equal to the square root of y. So that's how you solve, for example, this problem. Or you can write this instead of writing all of this notation. You can forget about x and y, meaning that provided that of course you know what is the argument of each of those functions, then you can simply write f inverse is equal to g. That you can write as well. But this is all provided that you understand basically everything about the problem. What is the argument of x, what is the argument of g, and so on and so forth. So that was question number 24.